This is our third and final lecture for the Introduction to Surfactants in Water. I've entitled this lecture Micelle Formation, Krafft Temperature, and Cloud Point. In addition to providing information regarding the efficiency and effectiveness at which surfactants accumulate at surfaces and interfaces, surface tension curves also indicate the onset of a process known as micellization. Often authors simply assume that the reader has a basic understanding of micelles, which is odd given that most undergraduates and even graduate students are unlikely to come into contact with self-assembly processes unless they're specializing in colloidal science. So we begin at the beginning by addressing a valid question. What are micelles? If we add enough surfactant to an aqueous solution, the surfactants begin to associate with each other to form clusters or aggregates containing tens to hundreds of surfactant species. The concentration required to initiate these interactions is quite low, usually on the order of a millimolar. This concentration is known as the critical micelle concentration, which is a property of the system, dependent on the temperature and the composition of the aqueous solution. The formed structures, which are on the micron size scale, are known as micelles. Micelles are thermodynamically stable clusters, which are a type of association colloid. Other association colloids include vesicles, microemulsions, and bilayers. The formed micelles have a common structural characteristic in that the hydrophobic tails of the surfactants are oriented away from the water, while the head groups are directed towards it. This is the classic model of a micelle, in which the hydrocarbon oil phase composed of the surfactant's hydrophobes is surrounded and isolated from the aqueous solution by the hydrated surfactant head groups and counterions in the case of ionic surfactants, which form a protective hydrophilic shell. Each micelle contains anywhere from 30 to 200 surfactant species. The number of species forming the micelle structure is known as the aggregation number, which is dependent on surfactant structure and solution conditions. Given that the shell of the micelle is what isolates the hydrophobes from the water, it is reasonable to assume that the area occupied by a surfactant's head group relative to the size of its hydrophobe should play a role in determining the architecture of the formed micelle. The classical representation of micellular geometry is of course that of a sphere. However, most evidence indicates that this may actually be the exception rather than the rule. A number of geometries are possible, including lamellar, inverted, disc, and cylindrical. It is likely that ellipsoidal discs and cylindrical structures are more representative of the norm. The critical packing parameter, or CPP, was developed to help predict the likely geometry of micelles formed for a given surfactant structure in a given set of conditions. The calculation of CPP requires three values. The first is the optimal area occupied by the hydrophil at the micelle-water interface, indicated here with a lowercase a and the subscript 0. This area term is governed primarily by the strength of the interactions between adjacent surfactants in the micelle. A second term required is the length of the hydrophobic group embedded in the micellular core, indicated here with a lowercase l, subscript lowercase c. This value is believed to be close to the maximum length of the hydrophobe when it is completely stretched out. Of course, it will never exceed this value. The third term required is the volume occupied by the hydrophobe within the micelle structure, which is indicated here with a lowercase v. The volume is a conic shape that connects the optimal area to the base of the hydrophobe. The critical packing parameter, CPP, is a ratio of this volume to that of a cylinder with a cross-sectional area of A0 and a length of LC. So what does CPP tell us? Well, surfactants with a large optimal surface area and a single unbranched hydrophobe, such as sodium dodecyl sulfate or SDS, under low salt conditions, will have CPPs of 1/3 or less. These species have a conic packing shape. Such surfactants typically form spherical micelles. Surfactants with small optimal surface areas in a single unbranched hydrophobe, for example SDS, at high salt conditions, have CPPs greater than 1/3. Within the range of 1/3 to 1/2, surfactants have packing shapes of truncated cones and typically form cylindrical micelles. Surfactants possessing multiple hydrophobes and/or small head group areas will provide CPPs between 1/2 and 1, and the packing shape of a truncated cone nearing that of a cylinder. Such species often form flexible bilayer micelles. As the CPP value nears 1, the surfactant will tend to form planar bilayers. It is important to keep in mind that CPP indicates tendencies, that is, an educated guess at the geometries that are likely to form. However, the same surfactant at different concentrations and different solution conditions can form an array of different phases. For those who study concentrated micelle solutions, CPP is an important value. However, if the primary goal is the traditional application of a surfactant, CPP is interesting but of little use. The sharp and sudden onset of micelle formation at a particular concentration, the critical micelle concentration or CMC, has the appearance of a precipitation process, which has led to its treatment as a phase separation. However, treating micellization as a chemical reaction, that is with the law of mass action, provides a similarly sharp and sudden increase in micelle formation at the CMC. For most purposes, there is little difference between these two treatments. However, there is experimental evidence that the monomer concentration does continue to rise beyond the CMC. Also, treating micelle formation as a reversible chemical reaction emphasizes the point that micelles are not permanent solid structures as they are often portrayed. Rather, their existence is fleeting, with surfactants continuously moving between their monomer form and the micelle structures. For a given temperature, the critical micelle concentration of a surfactant is determined by its structure and solution conditions. The sharp transition between monomers and aggregates at the CMC results in distinct changes in the properties of the solution, which allows for the determination of CMC using a number of different measurement techniques. For example, the formation of micelle particles, which scatter light, allows for the determination of CMC using turbidity. As will be discussed in a moment, the formation of micelles is what produces the inverse plateau on the surface tension curve. Thus, the onset of the plateau region in the curve gives us a way to identify the surfactant's CMC. In the case of ionic surfactants, the formation of particles substantially reduces the mobility of the added charge. As a result, a plot of solution conductivity versus surfactant concentration shows a break in its increase at the CMC. These are just a few examples of the various techniques that can be used in the determination of the critical micelle concentration for a surfactant. Next, we return to the surface tension data to demonstrate how the surface tension curves can be used to determine the critical micelle concentration for a surfactant. Here again is the surface tension data for the nonionic surfactant endodecyl beta-demaltoside. The focus is now on the plateau region, where the surface tension levels off due to a sharp increase in the kinetics of micelle formation. Often this region is improperly attributed to a saturation of the surface, when actually the leveling is due to the nearly complete consumption of the added surfactant to form micelles above the CMC. Such a leveling does not exist in the case of organic molecules that have amphiphilic structures but do not demonstrate the substantial surface activity of a surfactant. The normal alcohols discussed previously are a good example. These species lower surface tension, but the small size of their hydrophobic sections provides for only modest surface activity, and these species do not form micelles. As a result, their surface tension curves possess a gradual decrease in the slope of the solution surface tension with increasing solute levels, not a sharp and distinct plateau region. As with the previous properties extracted from surface tension curves, the plot of the surface tension versus the base 10 logarithm of the added surfactant molar concentration is the most convenient way for extracting the CMC value. The concentration at the intersection of the bottom of the horizontal line, the inverse plateau, and the line used to determine the effectiveness can be used to make this estimate. From this plot, it can be seen that the CMC of DDM would be reported as approximately 0.17 times 10 to the negative third moles per liter at 22 degrees C. Here again is the surface tension curve for the anionic surfactant sodium dodecyl sulfate, or SDS. Using the same approach as on the previous slide, its estimated CMC value is 8.1 times 10 to the negative third moles per liter at 20 degrees C. This is about an order of magnitude higher than that which was found for the nonionic surfactant DDM. This difference between a nonionic and anionic surfactant both possessing similar hydrophobes is a general finding. That is, the surfactant less comfortable in water has a lower CMC value. As discussed above, micelles form in solution once the added surfactant level reaches the critical micelle concentration. CMC is a property of the surfactant for a set of solution conditions. Values are typically tabulated for surfactants near room temperature in pure water. However, for many surfactants, there are data available for a range of temperatures and conditions. This slide reviews a few of the most important factors influencing the CMC of a surfactant. So let's begin. First, CMC is dependent on the stability of a surfactant in aqueous solution, and it is expected that CMC will correlate with measures of surfactant excess free energy in water. That is, for a series of surfactants belonging to the same chemical family, we expect their CMC values, or the logarithm of their CMC values, to correlate with parameters such as the number of methylene linkages in their hydrophobes, or their log KOW values. Next, more tightly bound counterions and increasing ionic strength tend to lower surfactant CMC by both decreasing surfactant stability in water and by screening the interaction between head groups for ionic surfactants. So salt both increases the driving force for the formation of the micelle, and in the case of ionic surfactants, it helps stabilize the formed micelle structure. Next, small organics can significantly influence the CMC via two possible routes. One route involves the organics becoming incorporated into the micelle to lower free energy of formation. This reduces CMC values. The second route involves the influence of the organic on water structure. For structure breakers, the presence of the organic will stabilize surfactants in the water phase, increasing their CMC values. Thus, in the first case, the organic actually helps stabilize the oil phase within the formed micelles. In the second case, the organic acts to break down the structure of water, increasing the stability of the hydrophobes. However, there also exists organic species which are structure makers, which will actually reduce the CMC values of surfactants. Finally here, the influence of temperature on CMC values is complex. Increasing temperature initially decreases CMC values by dehydrating head groups, but then increases CMC values with the breakdown of water structure. So in other words, it is often difficult to predict how changing temperatures will influence the CMC of surfactant species. Both of these plots are for surfactants from the same chemical family, alkyl alcohol ethoxylates, which we've discussed extensively. The lines demonstrate what was discussed on the previous slide. The maroon or dark-colored line is a correlation of the p-CMC values, that is the negative of the base 10 logarithm of the CMC values, as a function of methylene linkages composing the hydrophobes of the surfactants. Increasing the number of methylene linkages makes the hydrophobe larger and increases its hydrophobicity, which increases the p-CMC values, that is, it decreases the CMC values. The green line is a correlation between p-CMC values and the number of ethylene oxide linkages composing the hydrophils of the surfactants. This increases their hydrophilicity, which decreases their p-CMC values or increases their CMC values. It is interesting to compare the relative influences of these structural changes as quantified by the slopes of these lines. The addition of the methylene and the ethylene oxide linkages both incrementally change the p-CMC values, but the incremental changes are substantially greater with the increasing number of methylene linkages. Using the information reviewed on what factors control the critical micelle concentrations of surfactant species, let's go ahead and make a few comparisons. As with our previous set of comparisons, reported CMC values were measured in aqueous solutions for a single surfactant, and unless otherwise indicated, the data are for the addition of the surfactant to pure water. The first comparison is between SDS and dodecyl alcohol ethoxylate containing 4 ethylene oxide linkages. Given that the surfactants possess similar hydrophobes, it is expected that the nonionic surfactant will be less comfortable in the aqueous solution and thus possess a lower CMC value, which is consistent with the reported measurement results. The differences in CMC values here are quite large, almost 2 orders of magnitude. Here, 2 dodecyl alcohol ethoxylates are compared. The structure for the first contains 3 ethylene oxide linkages, while the second structure contains 8. Given that the addition of ethylene oxide linkages decreases the hydrophobicity of a surfactant, the first surfactant likely has the lower CMC value, which matches the reported values. The next comparison is again between two alkyl alcohol ethoxylates. This time, both surfactants possess the same number of ethylene oxide linkages, 8, but the surfactant on the right has a larger hydrophobe which contains 2 additional methylene linkages. This makes the second surfactant more hydrophobic, which provides it with a lower CMC value. This is consistent with the reported CMC values. These last two comparisons again demonstrate the relative influence of increasing the number of methylene linkages versus increasing the number of ethylene oxide linkages. Here the comparison is between sodium dodecyl sulfate, or SDS, and lithium dodecyl sulfate. Given that the lithium counterion is less tightly bound to the acid functional group, it is expected that SDS will have the lower CMC value, a conclusion that is confirmed by the experimental results. The second comparison is between sodium dodecyl sulfate, or SDS, and sodium dodecyl sulfonate under the same solution conditions. Previously, it was found that SDS was more efficient, implying that it was less stable in the aqueous phase. If this is correct, it is assumed that SDS should also have a lower CMC value when compared with its sulfonate analog. This is confirmed from the experimental results. The final comparison is between SDS under different solution conditions. The second aqueous system contains significantly higher levels of sodium chloride. This should decrease the stability of the surfactant's hydrophobe, that is, salted out, resulting in a lower CMC for the SDS under the conditions on the right. This is consistent with the reported CMCs. This slide provides a rough timeline for the movement to the surface of sodium dodecyl sulfate, or SDS, but it can be taken as an approximate timeline for most molecular surfactants. As surfactant is first added to the water, the surface tension drops sharply. The surface reaches 50% coverage within a 10 millinewton per meter decrease of the surface tension. The fraction of added surfactant that moves to the surface is negligible. Thus, the concentration of dissolved or monomeric surfactant is equal to the total amount of surfactant added to the aqueous solution. The tendency of the surfactant to accumulate at the surface relative to the bulk phase can be characterized in this region using the equilibrium constant from the Langmuir-Siskowski equation. As more surfactant is added, the surface tension continues to drop sharply. PEC20 values used to gauge efficiency are measured where the surface tension has dropped 20 millinewtons per meter. This corresponds to a surface coverage of greater than 80%, usually greater than 90%. With further addition of surfactant, the surface becomes saturated. The total amount of surfactant that can be placed at the surface is characterized by the maximum surface excess concentration, which is inversely related to the area occupied by the surfactant. Even with the surface saturated, the relative amount of surfactant that has moved out of the bulk phase is negligible. Thus, the concentration of dissolved surfactant is not significantly different from the total concentration of surfactant added to the solution. As the surfactant concentration is raised above the critical micelle concentration, the surface tension curve begins to enter its inverse plateau. As this occurs, the surface excess concentration remains near its maximum. Beyond the CMC, the surfactant introduced is consumed primarily to generate micelles. The surface tension remains constant, as well as the concentration of dissolved surfactant, which rises little above the CMC. Up to this point, our discussion is focused on characterizing surfactant adsorption. The approach we reviewed involves the experimental generation of a full surface tension curve and the extraction of PC20, gamma S max, and CMC values. These parameters gauge the efficiency, effectiveness, and truncation of the adsorption process at the water-air interface. Let's augment this discussion slightly by looking at the impact the adsorption has on surface tension. Because Gibbs' adsorption equation relates adsorption to surface tension, there is really no difference for much of the surface tension curve. We characterize adsorption efficiency by the rate of drop in surface tension, PC20. However, there is a difference when it comes to effectiveness. The lowest surface tension is not achieved at the surfactant's maximum obtainable surface excess concentration. After reaching its CMC, a surfactant has little or no impact on the surface tension. Thus, a reasonable estimate of the minimum achievable surface tension due to the surfactant is the value at its CMC, denoted gamma CMC. Gamma CMC gauges the extent to which a surfactant can lower surface or interfacial tension. It is an essential addition to our list of surface tension curve parameters because it has direct ramifications for the generation of colloids. For the other three parameters, we reviewed various qualitative relationships which allow us to predict their relative values. In the case of surface tension at the CMC, the connection between a surfactant's structural characteristics and the maximum reduction in surface tension it provides is less intuitive, with the assumption that when the surfactant concentration reaches its C20 value, surfactant nearly saturates the air-water interface. We can develop an expression to help us with this. This is an assumption that does not introduce a considerable amount of error. Considering Gibbs' adsorption equation, this is equivalent to assuming that the surface tension curve is linear for the log of the surfactant concentration ranging from C20 to the CMC. At these points, the assumption allows us to write linear relationships between the surface tension and the surfactant concentration. By subtracting one from the other, we obtain a relationship between the surfactants gamma CMC, C20, gamma S max, and CMC. The equation tells us that the extent of the surface tension reduction is extended by increasing a surfactant's maximum excess surface concentration, increasing its CMC, and lowering its C20 value. Using this to predict the relative extent to which a surfactant can reduce surface tension is somewhat challenging. Nevertheless, there are a couple of observations that can help. We are already familiar with what governs the maximum excess surface concentration. It's inversely related to the area occupied by a surfactant at the surface or interface. The ratio between CMC and C20 is always greater than 1, but predicting relative values is difficult. There are a couple of generalizations that can help. First, anything that makes the head group or tail bulkier raises a surfactant's CMC, but does not significantly impact the C20. The other is that electrical factors such as changes in counterions or ionic strength influence the C20 more than the CMC. Let's use this analysis to explain a few generalizations reported that connect surfactant structures to their limiting surface tensions in water. Starting with the observation that nonionic surfactants tend to have lower gamma CMC values than anionic and cationic surfactants. This is due to their higher maximum obtainable surface excess concentrations, their gamma S max values, and their bulkier head groups. Increasing the size of hydrophobes and decreasing the size of hydrophils causes a modest decrease in gamma CMC values. Such changes have little impact on the ratio of CMC to C20 and increase gamma S max values only slightly. Increased ionic strength and more tightly bound counterions decrease gamma CMC values. This is driven by the increase in gamma S max values and the stronger decline in C20 relative to CMC. Hydrophobe branching and the presence of multiple hydrophobes decrease gamma CMC values. This is due to the significant increase in the surfactant CMC. Increasing temperature slightly decreases gamma CMC values. This is primarily due to the influence of temperature on surface tension. Fluoryl and trisiloxane surfactants produce limiting surface tensions that are about half of that found with their hydrocarbon analogs due to strong chain interactions producing high gamma S max values. Anionic cationic complexes also provide quite low gamma CMC values due to the higher gamma S max values and bulkier hydrophobes. With this set of guidelines, let's compare some surfactants. The first comparison is between sodium decyl sulfonate and sodium dodecyl sulfonate in water at 25 degrees Celsius. We have increased the unbranched alkyl hydrophobe by 2 methylene linkages, which we expect to lower the gamma CMC, but only slightly, due mainly to the drop in the C20 value. The second example compares the minimum surface tension for ethoxylated fatty alcohol at 10 and 40 degrees Celsius. Based on our guidelines, the higher temperature should provide for a small drop in the gamma CMC value. For sodium decyl sulfonate at 25 degrees Celsius in distilled water and in water containing 0.5 molar sodium chloride, we expect the higher ionic strength to produce a decrease in the limiting surface tension due primarily to the decrease in the C20. You can see that the influence of ionic strength is relatively large. Next, gamma CMC values are compared for ethoxylated fatty alcohols possessing the same hydrophobe but differ in ethylene oxide linkages by 2. The number of linkages is above 6, so we expect a slight decrease for the smaller head group. This comparison is interesting. It's 2 sodium C18 alkyl sulfates at 25 degrees Celsius in water, with the second structure having a highly branched hydrophobe. The branched structure has a much lower limiting surface tension. This is due to its large CMC. Finally, we consider structures that provide extremely low limiting surface tension values. First shown is an anionic-cationic complex. When the chains are above 6 carbons long and about the same length, such structures provide high maximum surface excess concentrations due to the lack of head group repulsion and the interaction of the hydrophobic chains. Also contributing is the bulky multi-chain hydrophobe, which provides for a high CMC to C20 ratio. The next structure is a floral surfactant. The hydrophobes for such species are bulky, which inhibits the micelle formation while providing for a lower C20 value. Such hydrophobes interact significantly at interfaces, which provides for a substantial maximum surface excess concentration. A couple more surfactant properties that should be mentioned in our discussion are cloud point and Krafft temperature. Cloud point is a property of nonionic surfactants, primarily those possessing polyethoxylate head groups. Cloud points are measured by heating an aqueous solution containing a known concentration of surfactant, typically 1 weight percent, until the solution turns cloudy. This temperature is reported as the surfactant's cloud point. For a pure surfactant species, the transition is quite sharp, but for commercial products which often contain a mixture of surfactants, the transition temperature is more difficult to pinpoint. The cloudiness is a result of micelle destabilization. As the temperature is increased, the ethylene oxide linkages of the nonionic surfactants composing the micelles dehydrate, resulting in rapid aggregation. The increased light scattering from the formed aggregates make the surfactant solution nearly opaque. Cloud points are a view of a surfactant's phase behavior from a single perspective, that is, a single concentration and ionic strength. A more comprehensive view requires the development of a phase diagram. Cloud points are of interest because they're strongly tied to the underlying structure of the surfactant composing the micelles. This can be seen from the provided schematics, which show general trends for cloud points of alkyl alcohol ethoxylates. With a fixed number of ethylene oxide linkages, increasing the number of methylene linkages decreases cloud point, while fixing the number of methylene linkages and increasing the number of ethylene oxide groups increases cloud point. It is important to keep in mind that cloud point is not a determination of surfactant solubility. Rather, it's gauging micellar aggregation, a colloidal process. A detailed description of how surfactant structural and solution changes influence cloud point will not be provided here. In general, changes that decrease the hydration of ethylene oxide groups at the surface of micelle particles lowers the cloud point. Krafft temperature is a parameter that applies primarily to ionic surfactants. The figure is a schematic plot of surfactant concentration in aqueous solution versus temperature. The green line represents surfactant solubility, which for ionic surfactants increases with temperature. The red line represents the critical micelle concentration, which also increases with temperature, but the increase is more gradual. Thus, at some point, the curves intersect. The temperature associated with this point is identified as the surfactant's Krafft temperature. The Krafft temperature is more formally defined as the lowest temperature at which a surfactant will form micelles in water. A good way of thinking about this is that for temperatures below the Krafft point, the surfactant behaves like a typical organic molecule. As concentration is increased, the aqueous solution saturates with the surfactant and it precipitates out before reaching its critical micelle concentration. Keep in mind that surfactants are designed to be in part hydrophobic and tend to have low water solubilities. So below the Krafft temperature, little surfactant can be dissolved into the aqueous solution. However, after reaching the Krafft temperature, the surfactant begins forming micelles before reaching its solubility limit. Although in theory there is an upper limit to the amount of micelles that the system can retain, this limit is quite high and a tremendous amount of surfactant can be introduced to the system primarily in micellar form in this temperature region. The schematic shown here provides a general trend for the Krafft temperatures of sodium alkyl sulfates with increasing numbers of methylene linkages. It shows that the Krafft temperature increases as the size of the alkyl hydrophobe is extended, making the surfactant incrementally more hydrophobic. Increasing the length of the hydrophobe will lower the solubility curve, causing it to intersect with the curve for the temperature dependency of CMC at higher temperatures. Data for sodium alkyl sulfonates show the same trend. But it is interesting that these values are shifted to higher temperatures for the same size hydrophobes. In general, these curves demonstrate an important point regarding the selection of surfactants. As discussed, the more hydrophobic ionic species provide the greater efficiencies. This would indicate that the proper choice between surfactants is always those with the larger hydrophobe. However, it can be seen that phase behavior must also be taken into account when formulating complex systems such as emulsions and foams. If a surfactant is used below its Krafft temperature, little can be introduced to the system, and as a result, the surfactant provides little surface coverage and poor performance. This completes our chapter on the introduction to surfactants in water. These lectures were intended to provide an overview. There are entire textbooks dedicated to surfactant science. Hopefully our discussion sparked enough interest that you'll seek out more detailed information on these materials. The chapter began with an explanation of the origins of the term surfactant, and we discussed how surfactants are commonly broken down into different categories. This included a review of surfactant structure and an introduction to the term amphiphilic. We talked about how many surfactants are made and how they're named. We looked at the international surfactant market, including where surfactants are currently being utilized, and discussed how surfactants are selected for a given application. Next, the discussion turned to the behavior of surfactants in water. The Gibbs adsorption equation was introduced, which led to the Langmuir-Siskowski equation. The analysis of surface tension curves was reviewed, which provides us with measurements of surfactant efficiency and effectiveness. We talked about micelles, why and when they form, and their geometry. Finally, we discussed parameters that provide limited yet useful information on surfactant phase behavior, the cloud point, and the Krafft temperature.